So today I'm going to present the KiMoPack, which I've developed over 12 years, maybe in the past, after need. And when I started working with time-resolved data, I wanted to find a tool to plot something. Then we started modeling. And at that time, and also since then, I looked around and didn't really find something which works for me. So I developed KiMoPack for our group and then have shared the tools. You might call them beta user, but with a lot of befriended groups. And it has developed ever since, always after need. And it has become a quite nice round package, which I thought we can present here because for me, this is a reproducible and quite transparent way of doing data analysis. And maybe one extra thing about me in the parts is I'm sitting at Lund and part of Lund, which is focusing on nanoparticles, but we're also part of Lund Laser Center, focusing on laser-based spectroscopy. So a lot of the things I'm going to talk about today is based on time development of signals, time development of spectra, but not only, and I come to that in parts. Part of my work, however, also uses large-scale facilities, namely X-ray-based techniques, time-resolved X-ray spectroscopy. And KiMoPack was also developed to do parallel analysis using the same model and simultaneous refinement of X-ray and optical tools. So I also come back on that. So what is it in general? KiMoPack is actually an Python scripts as such, and I distribute them when they're freely available on the classical Python sources like PyPy or Anaconda. Also at GitHub if you prefer that. But there is a second part to that because scripts are usable by small numbers of people, and also it's if you're using script-based analysis, is A, not easy, and B, not necessarily always traceable on what steps you do in what order. And in order to make that easier and also usable for people who do not code as such, we developed a series of Jupyter notebooks. And I'm going to show you them in a minute live, how we use them. And those notebooks are developed for specific purposes. For example, in that case, I use the examples for transient absorption because that's the ones I'm providing for everybody. They start with single scan handling, which is fast. For example, one looks on the development of an experiment, sees how the sample changes. One is developed for plotting, where one creates nice looking, or I call them publication ready plots, shaping the data for plotting for publication. One could be for comparing different data sets, different analysis methods. One is for plotting, again, raw plotting, and then simple fitting. And one is for something more advanced modeling. The idea behind those notebooks is that each contains a set of codes or functions which are put in there, which are described. And for the user, it's a suggested workflow for the user. I develop many more notebooks for myself for each analysis task I do, but each notebook is its own freestanding unit, which I save with data, and I can actually publish with the data together on different platforms. Which brings me also to the things which are also KiMoPack as such. For one, there is a publication, which I've written together with Caroline Müller, in which we introduce the methods, what are used inside there. But we also, for example, discuss criteria. If one models data, what is actually a good fit? What is a good model? How do I recognize that? And I propose a number of criteria for that, which goes beyond just chi-square or R2 value, because there's actually more. Part of that publication is also in a series of tutorial notebooks, which are attached as PDFs to the publication, but are available as notebooks on GitHub, which is also where the code itself is published. And I think that's actually one, I personally think, very important part is the code I've written, which is KiMoPack, is given on PyPy, GitHub, or Zenodo, meaning everybody can download it, everybody can look, what are we doing, how are we doing that, even suggested improvements are there. And what I personally think is very important is that that code is, since it's developing with the part, there's frozen versions, and one PyPy or GitHub provides that, but also I'm using Zenodo meaning every time I create a release or a next official version, it is Zenodo takes that package, which includes the data, in this case, the example data, the analysis code, packs that and gives it the DOI. And this DOI I can cite from any paper. And that is unique and it cannot be changed once I have done that. Now, for publications, that would be a very neat way of actually publishing the analysis you have done by giving the notebook, which is unique for the analysis, together with the data and putting that on Zenodo. Then everybody can reproduce your analysis. In addition, since it is a bit of coding, there is an extensive documentation, and I've written 6,000 lines. So if I mean extensive, that's true. And this is just the documentation part. It's open source. There's a manual, there's tutorial notebooks, there's tutorial videos, and I'm still actively supporting people, for example, writing import scripts for the data. Now, I personally believe if you talk about code, we should show that. So I've prepared a little demonstration notebook. It is simply a copy of the workflow notebooks, and I would like to show how you work with that. So Jupyter notebooks are cells like this, which you execute and you execute code. And at any time, you can store those cells. And you can store those cells and you can print them, for example, as PDFs and can reuse them. Now I just do an import. For me, important that inside the notebook is also written which version I'm using. Somebody's talking in the background.
Sorry to interrupt, Jens.
Yes.
It's supposed to be something on the screen yes. Because it's now
okay. Then
white.
I share the wrong. Okay, then I'm sharing the wrong screen. I'm very sorry for that. 1 second. Thank you for the interruption. Let's new share.
So please, the others, mute your microphones.
Yes. Okay, I should have shared the screen instead of the presentation. So that's much better. No, you should see the screen, right? Yeah, very good. Thank you for the interruption. That was important. So this is the notebook, which you open in, and it opens the browser. I've just maximized the browser in this simulation. So this is in a browser, and in the background is running an interface, which you usually don't see. So if I work with these notebooks, I go to my data. Let's say my data is in the subfolder. I copy a version of the notebooks, and there's an interface how you can download them from the web. Or if you have developed one for yourself, I copy that somewhere close. And then I work inside that notebook. I give it a name, typically something related to my data. And I cancel that. And let me hide that part. And then I perform my analysis. In the notebook, it tells me the version, which is important to keep track. I open my raw data, and there's a neat GUI version where you can click on the data. There's a neat version where you can open the last data you have worked with. I personally prefer to actually type the file name and why I'm going to explain in a minute. And then I typically take a look at my data. And I do here some very quick shaping where I suppress scattered light and I suppress lines, but it's in a very straightforward way. And in here, what we have measured is we have measured a differential spectrum over time. And see a change of the spectrum. And I can very easily now plot, for example, the temporal slices. I can plot the spectral slices, and I can plot, for example, an SVD analysis of the raw data in a very fast way. Normally, if I perform the analysis, I would not plot that in the screen as I do it now, but I would plot that as a popped out window. But if I plot it in the screen as I do now, I can save the notebook with the images and, for example, attach this on a paper. In KiMoPack, I've chosen in way what can I import, because in many different places there are different data formats, different ways. For example, in order to show how we can import parts, I maybe also use the typical way how you ask in Python for help is if you take the import function and ask a question mark, you get the documentation. And there's every parameter you have is well explained and deeply given as examples. There are also example files, but I would like to highlight that I don't expect, or nobody, also I don't write that code fresh. I always use the notebook. I have example parameters in there and I just adjust them. But for media choices, I can import data in many different ways from one or two different files. I can have take external formats, adapt to pretty much any data format, because it is just coding. It is freely available. There's no limitation for that. I've also written in RPE, or in the programmable interface, where a small function can be written which converts any input. So now that is transient optical absorption, read from one set. With small import functions, you can choose, for example, single wavelengths dynamics. You can choose transient X-ray absorption, transient X-ray emission, transient Raman, streak gamma emission, or spectroelectrochemistry. For example, for spectroelectrochemistry, one would not use a time axis. One would, for example, use the current or the voltage one measures. The principle is the same. I have one spectral axis and I have one what is called the development axis. But let's really look at an analysis. Now in Jupyter notebooks, it's a feature of the notebooks, not of my program. I can plot the images as inline, or I can plot the images as a popped out version, which is easier for working with it. One would do that by using a switch called QT in that case. And the image pops out in that way. You can scale, you can change all the features of the image. So if one wanted to, one could click to your happiness. But more important, it's a way of working flexible with the program. In here, I reload my data. I filter the data, do some simple corrections. And for example, perform a chirp correction, which is a function I call. If you have done a chirp correction before, it uses old data. You can give it the numbers of the chirp correction or of the polynomial. If you have not done it before, something pops up and you can click to and first guess. I do a fast background correction. And then I come for me to the first part where I really plot all of the different options I want, these slices. And I can now change these plots. I have a set of parameters which are written in the notebook. So I can't remember. I also don't remember them all by heart. But that's why I have the workflow notebooks, because if I open the notebook, this is what I see. I can change, for example, relative wavelengths. So I can choose which wavelengths do I want to plot. Now I need to check. Yes. So which wavelengths do I want to plot the kinetics for? So I look in my 2D plot, I select the wavelengths, I type them in here. And yes, this is typing by hand, but this is just typing a few numbers, which I read from my plot. I change the times I think are interesting to look at, and I can work myself stepwise until I have a plot I like to use. And now that brings me to the second part, a plot I like to use. For what purpose do I do the analysis? Do I want to make nice plots, which I can put in the publication? Then, for example, I would change the name. I would describe a bit more. I would shape the axis. And that's one thing to do. If I would like to have a documented analysis, I use now here the sample name, which is just the file name. And I keep that one in the plot, because that tells me later, if I look on the plot, what I have done. If I really want to have interactive experiments, I can do that too. Now I can call an interactive plot, also with a single line, and play myself to different slices and do whatever I want. And the point behind that is it's transparency. That's the idea, because I set numbers of parameters which are suggested and documented and can be reproduced. And then I call a function, say, with these parameters, plot. But this does not mean that I change my data. What I do change is I change parameters and I give it a task to plot with the current parameters I have. So I don't touch my raw data ever. So at any time, I can, if I have those raw parameters, I can open up this notebook and say, run the notebook to that point, and I will have exactly the same result every single time. As long as I can open the file. And if you have used a GUI to open the file, if we talked here, you might have to click on the same data. If you have used the file name, you open exactly the same file. So this notebook is, in fact, your documentation. You go step by step through, set your parameters, and come to the point. I can save the project and save the data. Now, what that one does, it exports the data as raw data, as ASCII files, which you can now import in any other program for doing different type of analysis. If you don't like Python, copy that in Origin or any other program to make a plot. I can save the project, which saves the raw data, later also the fits, and all the parameters as parameters. So if I wanted to, I can just open up the saved file, which is an HDF5 file, which is this version I'm using. And with a single command, reproduce the plots, or with a single command, reproduce all of the fits. And that's all. I can take that file, put that one on Zenodo, and everybody can reproduce that. Lastly, and that's something I do every time, I can save a PowerPoint. Now that pops up with your windows, and maybe let me show you the output of that in these slides. That's the slide you're getting, which is just the sum of the 4 figures put on one single file. And I'm always plotting that and put it in an extra folder for fast references. That's the first purpose, making simple plots. It is completely reproducible because everybody can open the notebook and run the notebook to that point. It is traceable for me. And if you have a project where you have worked in or where you're working in, those parameters you typically set once. There's ways how to switch the axis, put energy on the bottom. There's ways how to shape, how to work with kilo electron volts. There's ways how to bin the data in very different ways. And all of that is very well documented, step by step, what is done if you chose those parts. But the philosophy behind KiMoPack is that everything what you do, you also see. So if you change the binning, then you see the binning inside that window. You see exactly what you bin. And the reason behind that is, if you use the same approach, that is what you use for the next of the analysis. If I create a plot for publication, I want to look at it in a special way. If I want to create data for further analysis, I create it in a slightly different way. If I want to compare data, I take even a third way. And that is what is for me, usually the next step is instead of, no, sorry for that. Something is happening here. This is usually the third way in which I, again, load one, maybe a second data set. I know I just need to find the plots. And I can plot the 2 different data sets with the parameters I have used up to now, and can compare, for example, data set 1 versus data set 2 as different measurements that can also be comparing different fits. Now, in here, there are powerful normalization functions where, for example, I can say I normalize to a specific spectral window, which is not in the plotting window, and can again compare the different data sets. For example, extracting what is the catalysis, what is my photo product, which I achieve after a time. I can compare times, or I can compare spectra. That one, at different time points. And for example, from here say, yes, this difference here is, for example, the sum of my photo product. Important here is this normalization, because that allows me to shift the data to the same level, and I can do that very controlled. Again, if I want to reproduce it, I just have to run the cell to here and run the cell, and it's documented while I'm doing that. So the code is stored, and I can print that. The same approach is true for fitting, and that's actually the one what I use most. I have again a notebook or a cell where I set the fitting parameters, and I, for example, use the output where I look on the SVD and say, okay, I have maybe 2 time points. Maybe I should bring, I can bring that back up. you want to change the code, that's absolutely no problem. TA, let's say we plot the raw plot again using the features, and I have plots. I have my 4 plots, and I can, for example, look on the SVD and read from there, okay, I have 2, maybe 3 time points or kinetics. I can make a first guess of where the kinetics are, or what are the dynamic points, and type my guesses in the data. Now let's close all the plots, and perform a fit. That one is now independent exponential decays. I have chosen in time region what to fit, and that time range, or in this case, a time range I ignore. I can choose a time limits and what to fit, and I can change that, because after the fit, I get a result, which is a number, and I can plot my fit output, and which is the kinetics. In that case, I create a model. I come to that in a minute. I create a model. I create and can compare, for example, measured versus calculated data. That one is 10 times the difference matrix. I can see my fits in my data set, again, for the same parameters I've chosen before. And I can play with that a lot. No, this fit doesn't work. Take that window. And maybe, for example, if you look in here, when one sees the time points I fitted, I've drawn them by line. There's an infinite time. There's one kinetic decay, which is maybe not quite as good. And if I look on the data again, I see that, yes, one of the kinetics wants to make an infinite fit, and one is something like 60 picosecond. Maybe that's not as bad. So maybe let's optimize my fit. So, for example, I add another parameter. In this moment, an infinite parameter. I make a copy of my object and fit that again. That was the fit, and I can now compare, for example, the 2 different models. Here, I can compare the 2 different fits at different times, and no, this is the wrong plot. Where is the plot of the comparison? Here. I compare the 2 different models, and one model had the name with infinite, which has an infinite feature, which is the brown and the green. And that one definitely reproduces my data. Now, this is a spectrum at a specific time, 1 in 10 picoseconds, and that one definitely reproduces my data better. So I can do a fit. I open up my data set. If I have set those shaping parameters before, I can come to that point in a fit, do a reproducible fit, which is a global analysis, within 30 seconds. If I have no shape parameters, if you have no choke correction before, it might take a minute to come to that point. So that is very fast. And all of the data, all of the parameters are in the plots. You can, for example, work on these plots. You can change your fitting parameters. You can change the fitting range. And I'm using in KiMoPack, I'm using LM-fit, which allows me, for example, to freeze a parameter. Say very false. False with an F. And then the parameter is locked. I can have a very flexible way of setting and working with parameters. Changing the model, for example, going from independent exponential decays to consecutive decays, is just changing the model name. And that's kind of what I would call common analysis for now. Now, that's the point where I think KiMoPack is special. Is what comes now is the next steps. Because what we have done up to now is we have parameters, do a fit, change parameters, do the fit, and we can play with it too. We can see how stable is that, how stable is the results I'm getting. There's a very straightforward tool, for example, for calculating error margins for each of the parameters. For that one, important is I change the parameter, optimize everything else, and do a standard F test. And I get reliable error parameters for the error values for my measured parameters. And when I did that first statistically safe test, I was very surprised how big that insecurity or how wide those margins actually are. But they tell you a lot about the stability of your model and how close are you to the real data. There are again ways how to, or simply save PowerPoint, is dumping those results into the into a slide. Again, my raw data, that's what I fitted. And that is my fit results, where I, again, put all of the results into a single slide, something for your files, something to keep track of. One gets decay-associated spectra, which is no details for this analysis, which don't matter. Going on, included are true global optimizers, which means they do a nail-the-meat optimization, which is the standard. And then I go to a different starting point, different starting point, different starting point, try to find the true global minimum. I can refine the arrival time correction or chirp, something which I have chosen in the very beginning. And where I want to spend the rest of the time I have is actually talking about other types of fitting. For example, I can include external spectra, which I have measured and use for an instead of calculating a spectrum, I can use an external spectra, so do something called linear combination analysis. I can fit multiple data sets simultaneously, something which I use a lot. For example, single wavelength measurements in spectra, different techniques, different pump wavelengths, multiple powers. Very useful, for example, for finding nonlinear processes for dynamics. I can put that one in as an option. Say these are 5 different data sets. I give each of them a weight. I don't have to. I can. I can say they have the same decay spectra. I don't have to. I can. I can say these parameters I want to optimize for all of them. These parameters are unique. I can set that. So I have very flexible ways of the fitting. And that is because this is just Python. So I can actually write anything. And that includes what I call external fitting models. And because what I talked about now is independent exponential decays. However, I can have external models which I describe. And I provide, for example, a library which contains the, I don't know, 17 or 18 most used models described in that way. I have different flows along different processes. You can simply load one of those functions and say, that's my model. You set the name of the parameters as your guess, and you optimize. There are models in there about different kinetic decays. There are distributed rates, nonlinear models, the classic ABC for a steady state. So, and you can write your own model, because in the end, a model is nothing but a Python function. Again, there are examples provided. And to give you a gist of what that actually means, and if nobody codes from their parts, it's maybe difficult to develop, but I also help people developing models if that's necessary. And again, you publish your model with it. You write a differential equation, which is at least what is often I do that. I numerically integrate the differential equations for different numbers of steps, give that a name, which is then used in the plots. And this is how I write a model, because with that, as soon as I can write a differential equation, I can write any model which flows. One can apply oscillation functions for coherent beating or similar parts. One can use, instead of assumptions, for example, here the assumption is I use a Gaussian pulse shape. I can write any other function in there, or I can use a measured function, for example, autocorrelation. One can combine different types of measured data. For example, and this is just a last picture I show, I can do use spectral electrochemistry, where I use the current of which I measured in my potentiostat as a model to describe how many molecules have been converted. And then, for example, in that image, I oscillated between over a wave, up and down many times, and I turn on and off a spectrum. The principle is the same. I have one development axis, one spectral axis, and I can model that. I can extract an decay associated, or in this case, species associated spectra, and then perform further analysis based on that. Now, that was a big overview, and that's an image which is summarizing that in an interesting way, maybe. I do an analysis for a purpose. I want to either create a plot, I want to understand, do a fast analysis, a quick fit. I want to do a deeper fit, or I want to compare different data sets. So I start with a purpose. And that purpose is what I provide workflow notebooks for, where I suggest that would be something you can do in that and that and that order. I provide the function names for that. And at the end of the day, if you've done your analysis, you save your notebook and you can publish that notebook. You can show you or the readers of your paper this notebook, and I maybe have the notebook from what we have just gone through looks like that. So that's the step-by-step analysis from what you do. How much documentation, how much text you write between those lines, that's of course up to you, how much time you want to spend. But the notebook is published, the PDF of it is published, the data is published. If you put that on Zenodo, that's what I call reproducible data analysis. Thank you very much.